Alright, now let's look at the final examination semester 1, 23-24. Okay, so we have part A and part B. So part A are objective questions and part B is the subjective questions. So question number 1. Okay, question number 1. So the term in the feminine left hand rules indicate what? Okay, so the answer is it indicate the force. Right? It indicate the force. You can do some searching in Google, so it will explain to you what is the direction of the thumb. Okay, what is the direction of the other fingers lah. Okay, you can look at it. So electric field will be maximum outside the conductor and magnetic field will be maximum inside the conductor. Okay, state that whether it is true or false. Okay, so that answer is true. Okay, maximum outside the conductor and magnetic field will be maximum inside the conductor. Right. Third one, choose the two major rules that can be used for the magnetostatic. So for the magnetostatic, focusing on the Biot-Savart's law and also the Ampere's law, right? Okay, so answer is B. So Ampere's circular law states that 1 over any closed path equal to enclosed by the path. Okay, so the answer is the line integral of the magnetic field. Okay, intensity, okay, equals to the net current enclosed by the path. Alright, question 5. 50 cm long conductor. Okay, so 50 cm represent the length. Okay, located at right angle. Okay, right angle means is 90 degree. Okay, to a magnetic field. Okay, magnetic field. Okay, calculate the flux density. Flux density is a B. Okay, of the magnetic field if a current of 5 ampere is the I. Okay, produce in the conductor produce a force on it of 1 nano, so of F. Okay, so let's look at all these variables. Okay, so you are required to find the B. Okay, so in this question they give you the information of the L, okay, the I, and also the F. So the equation that you could think about is the force acting on a current filament when the current filament is placed in an environment that has the magnetic field, okay, which is the line integrals, okay, of the currents, okay, cross with the B. Okay, cross with the B. This is the force. Right. So what you can do here is you plug in the formula. So you have the force, okay, and then you have the I, and you have the L, and you are required to find the B. Okay, so in this case we ignore the directions. We ignore the direction because it says that it is a right angle. Okay, so the length is right angle. Okay, so it means that it will produce maximums of force. Okay, so F you have 1 nano. Okay, current you have 5 and the length is 50 cm. Okay, 50 cm. Okay, and B you have to calculate. Okay, so you can calculate the B is 1 divide okay, so the answer is 0.4. 0.4 Tesla. Okay, so this question number 6, calculate the magnetic field density. Okay, the B. Okay, for magnetic strength equals to 1.5. So for this one, we have to apply these equations. Okay, this equation showing the relationship between the B and also the H. So mu naught you can get from the calculator, multiply 1.5. Multiply 1.5, yeah, you get this answer. Okay, ferromagnetic material include the following except Okay, so ferromagnetic material. Which one is not ferromagnetic material? Okay, so the answer will be glass. The glass is not a ferromagnetic material. It's categorized as the polymer. The magnetic field of a material is influenced by, influenced by what? H. Influenced by dielectric permittivity. Dielectric permittivity means this one. Dielectric permittivity, or the relative permeability, or the conductivity, or the electric field distributions. Okay, so the most suitable answer would be this one. Okay, the relative permeability, because the B is equals to this multiply this one. Okay. Question 9. Which equations below suit the sentence an isolated magnetic charge does not exist? Isolated magnetic charge meaning that something like this. You have a north pole isolated, okay, from the south pole. Okay, this is something that is not possible, because no matter how small, okay, is your magnetic field, you will have one side which is north and the other side which is south. So the magnetic flux will be from the north pole, okay, terminate at the south pole. So in this case, the magnetic flux density passing through the surface, okay, this is the surface, will be 0. Okay, will be 0, meaning that, okay, the magnetic charge, okay, will start from itself and terminate from itself. Okay, start from itself and then terminate from itself. It won't go outside the surface. Okay, so the answer is this one. Okay, so the magnetic flux passing through the surface will be equals to 0. Next, question 10. What is the meaning of a residual flux density BR in the hysteresis loop? Okay, so the answer is C. The magnetic field density of the material when the external magnetic field is equals to 0. Next one, we look at questions 11. Determine the magnetic field at the center of a square of the side equals to 5 meter and carry in 10 ampere of currents. Okay, so this is the case. You have a square. Okay, you have to find the magnetic field at the center. Okay, so the length of the side is 5 meter, and the currents, I assume it flow in these directions. Okay, it is 10 ampere. Okay, so it means that you have to break it into the 4 sides. Okay, so one will be from here to here. This is one side, and then second continue from here to here, and then third continue from here to here, and the last one is fourth to here. You have a 4 side of finite current filaments. Okay, so the equation for finite current filaments would be H equals to I over 4 pi r, okay, cos alpha 2 minus alpha cos alpha 1 and P. So you have to use these equations. Find H1 and then H2 and then H3 and H4. Okay? So I will draw the square here. okay, by putting the axis so that it is easier for me to refer. Okay, the length is 5 meters, so the point over here is 2.5, negative 2.5, right? So negative 2.5, and this is 5. So I assume my current flow in these directions. Okay, I assume myself. Okay, so I have a H1 here, H1, and then I have a H2 from here, H3 from here, and H4 from here. Okay, we look at the H1. Oh yeah, the observation point, okay, the place that you want to find the total magnetic field will be at the center, H1. Okay, so the equation is I over 4 pi r cos alpha 2 minus cos alpha 1, and it is phi. You need to find the r. Okay, define the t first. Okay, so t will be located along the line of H1. So all the H1, okay, their x is equals to negative 2.5. Okay, and the y will follow the observation point, okay, which is 0. So your r will be 0, 0 minus negative 2.5, 0. So it is 2.5 x. Magnitude will be 2.5, and unit vector r will be x. Okay, so next will be alpha 2 and alpha 1. So we will join the end of the line to the observation point. So this one will be alpha 2, and this one will be alpha 1. This is the point A, and this is the point B. Okay, point A and point B. So the length we know, right? This is 2.5, right? 2.5. And this is also 2.5. Okay, so we can find the angle here, right? So tangent 180 minus alpha 1 is equals to 2.5 over 2.5. Okay, so the alpha 1 is equals to 135. Whereas for the alpha 2, same thing. Okay, you know the length. Okay, the length here is 2.5. The length here is also 2.5. Okay, so you can get this angle. Okay, you can get this angle by using the tangent. Alpha 2 is equals to 2.5 over 2.5. Alpha 2 is equals to 45 degree. And now the H1, you can replace the value to be 10 over 4 pi r, 2.5, and cos alpha 2 minus cos alpha 1, and the phi is equals to dl. dl here, I assume the direction of the currents is in the y direction. This one I assume myself. Okay, cross with the unit vector r, x. So this one give me negative z, and over here I get 0.45. 0.45. This is the H1. Okay, we continue to the H2. H2. So I erase the H1 first. H2. Okay, H2. Right. So H2 will be this one. Okay, H2 will be this one. Then I connect it. Okay, so the unit vector R will be y directions, and the magnitude of R is 2.5. Okay, so this one will be the alpha 1, and this one will be the alpha 2. Because it is the same directions. Everything is the same directions except for the I is not same directions. Okay, but the angles, everything, so it has the same dimensions. 2.5, 2.5, everything. So here overall, I can say that for the H2, the R is 2.5. Okay, unit vector R. Okay, unit vector R, you look at the directions of this arrow. Okay, so this arrow is pointing down. Okay, it's negative y. Okay, negative y. Okay, so the alpha 2. Okay, alpha 2 is equals to 45, same like H1. Okay, and alpha 1 is equals to 135. Okay, the same thing. So my H2, okay, will be 10 over 4 pi r. Okay, so this is cos 45 minus cos 135. Okay, so the current now, okay, you can look at the current, how the current flow. Okay, current flow in the x directions. Current flow in the x directions, cross product, okay, with the R is a negative y. It's negative y. So xy, you get z. So this is also negative z. Okay, so negative 0.45. So based on the trend here, we can actually expect it is the same for the H3 and also H4. Okay, so I will just multiply 4 to get the HT. So the HT will be 0.45 times 4 is 1.8 negative Z. Okay, amperes per meter. So you can look at it. Okay, so magnetic field, okay, this is the H. Okay, so the answer will be 1.8. Okay, so the negative Z is actually the directions. Okay, the directions. So they only want the magnitude, so we pick the D. Calculate the induced EMF. Okay, so you can write down EMF. For N equals to 10, and the flux change over time is this one. Okay, is this one. Okay, first of all, we are quite sure about this is a transformer EMF because it gave us the turn, right? Okay, and the flux change over time. Okay, so it is a time varying magnetic field. So the equation for this will be equals to negative N dt b dot dx. The flux change over time, I think, should be equals to dc dt. Yeah, it's not a dq. It's not a dq. Right, so it means that this one is equals to 0.5. Okay, so if you multiply with 10, okay, you get 5 volt. So the -5 is actually representing the direction of the current flow according to the Lenz's law. Okay, we were just talking about the magnitude. Okay, so this is a 5 volt. The variation of flux with time may be caused in 3 ways, except by having a stationary loop in a time-varying B field. Having a stationary loop in a time-varying B field. By having a time-varying loop area in the static B field. Okay, if you look at the option A, B, C, all of them are the criteria to generate the generate the EMF, except for the D. By having a stationary loop in a static B field. Okay, so the answer is D. The concept of displacement current was a major contributor to Maxwell. Okay, identify which of the following expression is Maxwell equation. Okay, if you remember the 4 equations in the Maxwell table, okay, so this one will be the answer. A loop is rotating about the y-axis in magnetic field B. Okay, so you have a y-axis over here. For example, this is your s-axis. This is your y-axis. This is your z-axis. And you have a loop. Rotate it. You just imagine this thing is rotate it about the y-axis. This is the loop. Okay, it rotate. The voltage induced, okay, in the loop is still do the is still do what? Is still do the motional EMF. We are very sure. This one also, no, I think it's the typo. It should be motional. It's not transformer, and this is not true also. Okay, so in a magnetic field B, it doesn't mention whether it is a time varying or not. So I think the answer is A. Okay, motional EMF. Electromagnetic waves are longitudinal, transverse, okay, both longitudinal and transverse, and none of the above. Transverse, that is the answer. Okay, so an electromagnetic wave is traveled to the east at a given point, E vector point, straight up. What is the directions of the vector B? Is straight up, transverse in the east. Okay. This is north, this is south, and this is east, and this is west. Okay, traveling to the east. Okay, so traveling to the east. Okay, so is these directions. Okay, E vector points straight up. So what will be the directions? What will be the directions? Okay, so the direction will be 90 degrees. Okay, so it will be going down here. Okay, south. What is the wavelength of light if the frequency is 200 terahertz? Okay, terahertz. Okay, so wavelength. Okay, so we use this equation, C equals to F lambda. Asking for the lambda. Okay, this one is tera. Okay, terahertz is 200 times 10 power 12. Okay, so you can calculate. So this is 1.5. Okay, microwave spectrum range from 300 megahertz to 300 gigahertz. Following are the applications of microwave radio accept. Okay, accept what? Telephone call. Yes. Bluetooth. Yes. WiMAX. Yes. And none of the above is not the answer. Okay, means the other three are the applications of microwave radio. Okay, so we will go to the part B subjective questions. Question number 1A. So you have a finite long wires carry 2 ampere of currents. So you have the I towards the y direction and stop at this position from the origin. Okay, so you have the magnetic flux density B, and you have to calculate the F, which is experienced by the wires that carry the currents. Okay, so we can list down what is the informations that we have. So we have the I, right? We have the B. Okay, so this one is telling us the length. Okay, the length. Okay, right. So you have to calculate the vector force. Okay, vector force. So we need to figure out what is the equation that we will use. Okay, to find the force acting on the current elements. So we'll be using these equations. F equals to integrate I dl, okay, cross B. So this is the equation to find the force. Yeah. Okay. So integrate I, we have that is a 2 ampere. So dl stands for the length of the current filaments. Okay, if you want to have better illustrations, you can draw the current filaments. Okay, so the currents starting from the origin until 20. Okay, so start from the origin and stay until 20. Okay, until 20. Yeah. Okay, so this is your I. Okay, so this is the z-axis, this is the y-axis, this is 20. Okay, so the B is in the negative z direction, so the B is going down like this. This is the B, B going down. Okay, so the length of the current filaments, okay, is dy. Okay, so dy in the y directions. Okay, in the y directions, and the B so for the B is negative 2.5, negative 2.5 in the z directions. Okay, next we define the interval. So the interval, okay, of the length of the current filament is from 0 until 20. Okay, 0 until 20, you see, 0 until 20. Okay, so let's calculate this. Right, so you can key in the calculator, integrate 2.5 multiply 2, okay, and from 0 to 20, so you get 100. Okay, 100 is the value. So yz, okay, yz you get x, okay, negative x over here, right, negative x over here. Negative x is the directions. So the answer is negative 100 x newtons. So this one will be the force acting on the current filaments. Okay, go to the next questions. All right, so now question B. You have an infinite long coaxial cable that has a hollow inner conductor of radius A, which has a cladding of radius B, okay, which is a magnetic material of permittivity mu as depicted in the figure 1.1. Okay, so there is a figure 1.1. Okay. Okay, so this is figure 1.1. So the inner conductor carries the total supply current I, and the outer conductor carries the total return current I. Okay, so inner conductor, okay, inner conductor is this one, okay, inner conductor, and outer conductor is over here, okay, outer conductor. Okay, so both are distributed uniformly around their respective cylindrical surface in the direction indicated in the figure 1.1. Okay, 1.1, you see, okay, the arrow is going up for inner, and for the outer, the arrow of the current is going down, going down. State the law that can be used to calculate the magnetic field everywhere. Okay, so you want to calculate the magnetic field. Okay, so magnetic field is under chapter 2, magnetostatic. So we learn two laws. That is the Ampere's law and also the Biot-Savart's law. So in this case, okay, we will use Ampere's law. So you can just write your answer as Ampere's law. Okay, so next one is calculate the magnetic field intensity everywhere in the region in between A and B. Okay, all right, see, A is here, B is here. All right, B is here, and B is here. Okay, so you have to calculate the magnetic field here. All right. And to have a better illustrations, I think we need to draw again, because this figure is a bit blur. Okay, so we have A here, and we have a circles B here. This is A, and this is B. Okay, and in between A and B we have the mu. Okay, and outside we have another circle. Okay, that has the radius of C. Okay, radius of C is over here, C. Okay, and mu naught is over here. So everywhere in the region in between A and B, okay, in between A and B, yeah. So this one we could have the possibility that the rho, okay, is less than the A, because it's everywhere, right? So it is possible, okay, rho less than A, and then the rho is in between A and B. Okay, so we'll be finding the formula of the magnetic field in these two regions. Okay, so we go to the region number 1 first. So region number 1 is the rho that is less than the A. Okay, rho less than the A meaning that this part. Okay, so I will draw again. I'll draw again. Make it bigger a bit. Okay. Okay, so this is the A. Okay, look carefully, this is the A, and now I make it bigger. So you want to find the magnetic field, okay, in these regions, meaning that you want to find the magnetic field at all these points, okay, that is less than the rho. Okay, so the first thing you have to do is you have to form an ampere path. Okay, you have to form an ampere path. Okay, so we'll apply the Ampere's law. So the Ampere says that if we integrate the magnetic field, okay, in a closed loop, this is a line integrals of magnetic field, we'll be getting the current that is enclosed, okay, by the Amperian path, or current that is enclosed by the Amperian path. Integrate, okay, line integrals of the magnetic field, okay, in the closed loop is equals to the current that is enclosed, okay, by the Amperian path. So this is the definitions of the Ampere's law. So if you look at the inner conductor, okay, so we want to find the magnitude at the region that is we will say the radius, okay, the radius is less than the A. So the current that is enclosed by the Amperian path, okay, will be less than A. So we need to find out what is the current here. Okay, so to find this current, okay, we have to recall back what is the relationship between the currents and also the current density. Okay, so this one is the relationship between the currents and the current density, the J, okay, the J. Okay, I equals to integrate J dot ds. Okay, so we will have a double integral because it is ds. So the J, so the dx for cylindrical coordinate will be r dr dphi. Okay, and the radius will be from 0 to A. So A is the radius of the inner conductors, and the dphi will be from 0 until 2 pi. Okay, 0 until 2 pi. Okay, so if we perform the integrations, we will have a J, okay, r squared over 2, right, and then we replace it with A and 0, and 2 pi. Okay, and 2 pi. So we will have J multiply A square pi, and this is our I. So our J will be equals to I over A square and pi. Okay, so this is our J. Okay, so we are going to apply this J over here in this case, okay, at the position where we want to find the magnetic field. Okay, so let me shift this one a bit. Let's shift it here. Okay, so we focus this one. Okay, so for the left hand side, okay, we'll have an integrate. Integrate this one is a H. So H in the phi directions. Dot product. Okay, so dot product with by using the cylindrical coordinate. Cylindrical coordinate. So will become r d phi. Okay, will become r d phi. Okay, and for the right hand side, we have an integrate, okay, the current density ds. And the ds here later is the r d theta. Okay, this one I forget to put the phi. Okay, I forget to put the phi. So this one and this one will become 1, and the phi is from 0 to 2 pi, and this one 0 to 2 pi also. Okay, so this is going to be replaced by r d theta, d phi. Okay, so the r will be from 0 to rho. Okay, rho is the position that we want to find the magnetic field. Magnetic field. So we'll be taking the j from this one, from here, the j. Okay, so 0 to 2 pi, 0 to rho. Okay, 0 to rho. I over a square pi r d phi. Okay, and for the right hand side, it is h r and 2 pi. Okay, this one we did before. Okay, so this one will be equals to, okay, we can take all these things out. I over a square pi. Okay, so you integrate, this would be r square over 2 rho 0 and then 2 pi. So the 2 pi here you can cancel out. You can cancel out. Okay, you can cancel out. Okay, so you will have I rho square over 2a square pi. Okay, 2a square pi equals to HR. So the R over here, you have to replace it with the rho. Okay, have to replace it with the rho because it will be the place that you want to find the magnetic field. Okay, position to find the magnetic field. Okay, so you can cancel this one with this. So the magnetic field will be I rho over 2a square pi. Okay, and in the phi directions. So this is the magnetic field when the rho is less than a. Okay, rho less than a. Okay, we'll move on to the positions in between A and B. Okay, and B. Okay, and B, this is the positions. Okay, so A is here. Okay, if you still remember the drawing. Okay, B is here. Okay, and this is mu. Okay, so now you want to find the magnetic field in between. Okay, so you have to form the Amperian path. Okay, so Ampere's law say that if you integrate the magnetic field, okay, the line integrals of the magnetic field in the closed loop will be getting the current, okay, that is enclosed by the loop. Okay, so in this case, you can see the red color Amperian path is enclosed completely the inner conductor A. Okay, so the I, okay, so I will remain the same thing. Okay, you don't need to go to the integration of current density. Okay, so it will become integrate 0 to 2 pi. Okay, h phi, then you have a r d phi. This is what we usually do. And I is this one. Okay. So you will have a h r 2 pi equals to the I, and your h will be equals to I over 2 pi r. Okay, so this is the equations of the magnetic field, okay, when the radius is in between A and B. A and B. Next, we move on to the next questions. Okay, calculate the magnetic field intensity in the region in between A and B with material mu r equals to 1. The question actually want B, want us to find the B. So what is the relationship between B and also the H? Okay, so this is question number 3. Okay, so the B is equals to mu H. Is equals to mu H. And the mu actually is the mu naught multiplied with the mu r. Okay, so just now you mentioned that the mu r is equals to 1, right? 1. So we only have this mu naught. Okay, so B is equals to mu naught multiply the H. So it will be mu naught multiply the H. So the H is I equals to 2 pi rho. Okay, 2 pi rho here. 2 pi r, sorry. So the 2 pi r. I think I should use rho, right? Or rho, because this is rho, so this one is also, I will use the rho. Otherwise, very confusing. Rho. Okay. So the direction is phi. Okay, so the direction of phi. So this one will be the answer. Alright, so now this is question number 2. So this is a question that we have tried before. Okay, one of the questions, okay, in our module. So I will discuss this question 2a. So we move on to this question B. Question B. So you have a conducting bar move to the y direction with a velocity u through 2 conducting rail as shown in the figure. Okay, so you can see here you have a 2 rail. So you have a 2 rail and A, B, okay, you can move it, okay, in the directions of y. Okay, so the first question is you have to state the name of the electromagnetic force generated, okay, electron EMF, EMF generated if the conducting bar is in the stationary and moving conditions. Okay, so if it is stationary, okay, so if it is stationary, okay, and if the B is time varying, okay, this is the B. Okay, if the B is time varying, so this one will be transformer EMF. So you can write down transformer EMF. Okay, transformer EMF. Whereas when the conducting bar is in the moving conditions, so if it is moving conditions, so this one will be motional EMF. So you could write down it as a motional EMF. Okay, so this is the answer for question number 1. Okay, so we go to question number 2. Find the electromagnetic force, okay, on the bar, okay, EMF on the bar if the bar is located at the position y equals to 4 centimeter and the B is this, okay, You see here is a milli, yeah? Okay, milli. So when you look at here, the bar is located at a fixed position. This one is a fixed positions, meaning that it is not moving. And if you look at the B, okay, and the B is time varying magnetic flux density. Okay, so this one is obviously a transformer EMF. Okay, transformer EMF. So for transformer EMF, the equation that you have to use is equals to negative n integrate B dot ds. Okay, so this one is the equation that you have to use. So in this case, when you refer back to figure 2.2, you can see that, okay, the n is equals to 1. You don't have many coils. Okay, so the n is equals to 1. So you can erase this n because it is equals to 1. Okay, now let's do the integrations first. Then only we do the differentiations. So the integrate. Alright, so now the what information we have? Okay, so the bar is located at a position 4 centimeter. Okay, so this one we will assume it is actually connected. Otherwise it can't form the loop. So this one is at the positions of 4 centimeter. 4 centimeter, which means is 0.04 meter. Okay, and this one is 8 at centimeter. At centimeter. Okay, 0.08. Okay, so this one will be the surface. Okay, surface of the flux passing through. Okay, so the B, you can put it as 2 cos 10 power 6 T. And this is milli. Okay, don't forget the milli. I put the milli in front. Okay, Z directions. Dot product with the, okay, so you have a dx, dy. Okay, this is the ds for Cartesian coordinate. And then the direction is also Z because the surface is facing the direction Z. Okay, interval of the dx will be from 0 to 0.04, no, 0.8, 0.8. And then for the dy is 0 to 0.04. Okay, so this one is equals to 1. Right. Okay, so let's integrate. So you will take this 2 milli cos 10 power 6 T. Okay, take it out because it doesn't relate with the integrations. Then you have 0.08. Okay, when you integrate dx, and 0.04 when you integrate the dy. Okay, we'll integrate the dy. Okay, so let's keep this thing better first before we perform the differentiation with respect to the t. So your 2 milli multiply with 0.08 multiply 0.04. So you have a 6.4 times 10 power negative 6. So you differentiate the cos, you get negative sign. So negative sign become positive sign. Okay, so differentiate, end up you have to multiply it, right? Yeah, differentiate, multiply it. So you multiply 10 power 6. Okay, so this one will be balanced up. Okay, when you balance up, this one means that it will become 6.4. Okay, sine then 6 NT volt. So this one is the transformer EMF. Okay, transformer EMF. Okay, we go to the next one. Okay, determine the electromagnetic force, okay, on the bar if the bar moving. Okay, you see moving, moving, okay, with velocity u, okay, in the y directions, okay, y directions, okay, and your magnetic is 4 milli in the z directions. Okay, so when the bar is moving, so now you will have a motional EMF. Okay, motional EMF you have to find. So for this one, we're going to find out the motional EMF. So for motional EMF, okay, so the equation that you have to use is integrate U cross B and then dot dl. So dl stands for the length of the moving bar. Okay, so u, okay, u is 10 in the y directions, cross with the b, okay, b is 2z, mentioned by the questions. So the bar, the moving bar is in the x directions, x directions, so it will be dx. Okay, why it is x, you can refer here. This is your moving bar, right? Okay, so your moving bar length, the length of your moving bar is follow the dx. Okay, so it is dx and x directions, x directions. Okay, regarding the length, right? Regarding the length, you have to, regarding the interval, okay, you have to determine first the direction of the currents. Okay, so now this is your original magnetic flux density. So the current will produce another magnetic flux, okay, that oppose the directions. So as the result, okay, your current flow in this way. So you have to integrate opposite the directions of the current flowing, that is from 0.08, okay, to 0. Okay, you have to follow these directions. Okay, so you integrate 0.08 to 0, oppose the direction of the current flow. So here you will have a 20, okay, 20. So yz will give you x, okay, and over here you still have one more x, so you can cancel both of them to make it 1. Alright, so this is the things. Okay, so you will get this negative 20 multiplied 0.08, you get negative 1.6. Okay, so don't worry about negative. This just to show you the direction of the current flow that is opposed, okay, the directions of the magnetic field, okay, that the original magnetic flux density. Okay, so this one is the motional EMF. Okay, motional EMF. Right. Okay, so this is question number 2. Okay, we go to question number 3. Okay, this is question from chapter 4. Okay, chapter 4. The electromagnetic wave can propagate over different type of medium. Okay, this is what we discussed previously in chapter 4. Okay, so differentiate the characteristic of the EM wave in the following media in terms of conductivity, permittivity, and permeability. So the electromagnetic wave can propagate in the lossy mediums, okay, in the lossless medium, a good conductor, and free space. So the question want you to list down what is the characteristic of its conductivity, permeability, and permittivity. Okay, so you can list down, okay, what is the characteristic for lossy. Okay, so for lossy medium, okay, so for lossy mediums, the conductivity is not equals to 0. You can refer to your notes, this one is in your notes, and for the epsilon, the permittivity is equals to epsilon r and epsilon naught, and the permeability is equals to multiplications of mu r and also the mu naught. Okay, so this one is for lossy mediums. Okay, as for the lossless, okay, lossless medium. So for lossless mediums, okay, one thing that is very important is the conductivity is approximate to 0. And one thing that you can prove whether the medium is lossless or not by comparing its conductivity and check whether it is less than omega multiplied with the epsilon. Okay, if this is correct, then this is considered as a lossless. And for this one, it is equals to this, and for the mu is equals to mu r and mu naught, and mu naught. Okay, so this is the lossless. Then we have a good conductor. Good conductor. Okay, so for good conductor, the conductivity will be very, very good. Okay, approximate to infinity, very high. Or we can say that, okay, the conductivity is, as long as it is greater than omega epsilon, then it is a good conductor. And for this one, okay, it is equals to mu naught. There is no mu r for good conductor. And for the permeability, it is equals to mu naught multiplied with the mu r. Okay, so this is the characteristic of the good conductor. And lastly, we have a free space. Okay, free space. So for free space, the conductivity is equals to 0. Epsilon is equal to epsilon naught. Mu is equals to mu naught. Okay, so these are the characteristics of 4 different mediums, okay, that the wave can propagate. Alright, we go to the next questions. Okay. Okay, so now seawater plays vital role in the study of submarine communications. Okay, so given that the characteristic for seawater, okay, are all these, okay, seawater. Okay, so you have to calculate, okay, and determine the following terms. So whether the sea is a good conductor or good dielectric, okay, and then find the attenuation constant. Okay, so this is what you have to find out. Okay, so what is good conductor? And go to here. Okay, when it is considered good conductor, and the conductivity is greater than omega multiplied with the epsilon. Okay, if this is correct, then it is a good conductor. So you have to prove it out. You have to prove it there. Okay, so how to prove it? So for the first one, okay, you can mention good conductor, okay, has the characteristic that the sigma is greater than omega multiplied epsilon. Okay, so what is omega? The conductivity is what? Conductivity is 4. Okay, it's greater than omega is 2 pi f, and you can see the f is 100k. Okay, and the epsilon is 80. Okay, 80 multiply epsilon naught. So you can calculate this 2 pi multiply 100 multiply 80 multiply. Okay, so 4, of course, it is much more greater than 4.45 times 10 power negative 4. Okay, so when this is correct, this is true, we can say that, okay, the seawater, okay, the seawater is a good conductor. Okay, so what happens if it is a good conductor, then find the attenuation constant. Okay, so you can refer back to the formula, attenuation constants. Okay, for good conductor, it is the same as the phase constant. It is equals to omega multiply mu conductivity and divide 2. Okay, or there is another equations, right? We have the other equations, that is pi f mu and sigma, right? This is the other equations. So in fact they are the same, right? Because this omega is 2 pi f okay, so it depends on which one you want to use. Okay, which one you want to use. Okay, so if you want to use the second one, you can replace the pi, so you have 100k. Okay, and your mu, okay, your mu is 1. Okay, so you have a mu naught. Sigma is equals to 4. So right, square root, then you get this 1.26, right? 1.26. Okay, so this one is your attenuation constant. Okay, next we look at the phase velocity. Okay, the phase velocity. So for the phase velocity, okay, the symbol is this one, the u. Okay, u equals to omega divide beta. So the omega is 2 pi f. F is 100k. And the beta is 1.26 because it is the same as the alpha. Okay, so you can calculate it. Okay, the answer is 5 times 10 power 5. Okay, so this is the velocity, so the unit is m over s, velocity. Then we go to the third one, is the wavelength. So you can find the wavelength by using these equations. Okay, the relationship between the wavelength and also the beta. So you have a 1.26, and you can easily get your wavelength. Okay, your wavelength is 5 meter. Next one is the skin depth. Okay, the skin depth, the symbol for the skin depth is this, the delta, and it is equal to 1 over alpha. Okay, so your alpha is 1.26. Okay, alpha is 1.26, so you get this 0.796 meter. Okay, as your skin depth. Alright, so this one is the solutions for the final exam. Okay, semester 1 to 23 and 24, 2, 3, 2, 4. Okay.